Nuclear magnetic resonance, often called NMR, is a spectroscopic tool which has come to have wide use in structure determination and chemical analysis during the last few years. It can provide many kinds of information about the structure of molecules. This film gives an introduction to the theory of NMR and a few of its applications. We all know how a compass behaves. The needle lines up in a magnetic field. Any other alignment is of higher energy. The nuclei of certain isotopes are magnetic and behave like small compass needles. If these nuclei are placed in a magnetic field, they tend to line up with the field. The strength of the field is shown by the closeness of the lines of force, and the direction of the field is shown by H0. For many nuclei, the quantum theory allows only two alignments, with the field or against the field. These two alignments have different energies. As with the compass, with the field is lower and against the field is higher, since it takes work to turn a magnet against the field. The energy difference between these two alignments is proportional to the intensity of the applied magnetic field. If the intensity of the field is doubled, so is the energy difference. There is also a temperature effect. At absolute zero, all nuclei would be aligned with the field. But at room temperature, thermal energy is large, and only a few more nuclei are in the lower energy level than in the higher. At room temperature in typical magnetic fields, for every million nuclei in the upper level, there are 1,000,006 in the lower. In NMR, as in other types of spectroscopy, transitions between energy levels are caused by absorption of electromagnetic radiation with a frequency, nu, equal to the energy separation, delta E, between these levels. Radiation which corresponds to delta E is in the radio frequency region. When this exact frequency is applied, some nuclei in the lower level absorb energy and jump to the higher level. This behavior is called resonance. NMR experiments can be carried out either at constant magnetic field or at constant radio frequency. If the magnetic field, and thus delta E, is held constant, we can vary the frequency. When the energy matches delta E, resonance occurs, and nuclei jump from the lower to the upper level. If the frequency of the radio signal is held constant, we can vary the magnetic field until delta E becomes equal to the energy of the radio frequency, and nuclei jump to the higher level. Thus, we can cause resonance by varying either the radio frequency or the magnetic field, holding the other constant. How is an NMR experiment carried out? The sample, which must be a liquid or a solution, is placed between the poles of a powerful magnet. A radio signal is applied from a transmitter. If the experiment is done at constant magnetic field, we vary the transmitter frequency. When the energy of the radio frequency equals delta E, some nuclei absorb energy. If we are working at constant frequency, the magnetic field is varied until delta E equals the energy of the radio frequency, and the nuclei absorb energy. In both kinds of experiments, energy absorption is detected by a receiver and appears as a peak on a recorder chart. Let us have a closer look at the sample. At constant field, the radio frequency is varied, and an absorption peak is recorded. If the radio frequency is constant, the magnetic field is varied, and a peak is recorded. is only the ratio of frequency to field that determines where resonance occurs. This ratio is called gamma, the gyromagnetic ratio. The magnetic properties of each isotope are different, and each isotope has its own characteristic gyromagnetic ratio. Some of the isotopes which can be studied by NMR are protons, fluorine-19, phosphorus-31, and carbon-13. With a fixed field, for example 14,092 Gauss, the gyromagnetic ratios of these isotopes give rise to characteristic resonance frequencies. Protons resonate at 60 megacycles per second, fluorine-19 at 56, phosphorus-31 at 24, and carbon-13 at 15. Frequency is usually plotted increasing toward the left in NMR. Some isotopes, such as carbon-12 and oxygen-16, are not magnetic and cannot be studied by NMR. At fixed frequency, for example 60 megacycles, magnetic isotopes resonate at characteristic fields. Magnetic field is usually plotted increasing to the right in NMR. By far the most important isotope for NMR studies is the proton, which in a field of 14,092 Gauss resonates at about 60 megacycles. Unlike protons in empty space, protons in molecules are somewhat shielded from the applied magnetic field by the surrounding electrons. The amount of shielding depends on the electron density around the proton, which is decreased by electron withdrawing groups. As electron density around the proton increases, a stronger magnetic field is needed to overcome the shielding and make the proton resonate. If all protons had the same shielding, they would all resonate at the same field or frequency. However, protons in different chemical environments are shielded differently. Slightly different values of either applied field or radio frequency are required to make them resonate. With saturated hydrocarbons, for example, at 14,092 Gauss, the protons in CH2, or methylene groups, resonate at about 60 million and 75 cycles, while protons in CH3, or methyl groups, resonate at about 60 million and 54 cycles. This difference is called the chemical shift and amounts to only a few parts per million. Since it is difficult to measure the absolute ratio of the frequency and the magnetic field accurately enough, a compound is usually added to the sample as an internal standard. Tetramethylsilane, often called TMS, is commonly used. Its protons resonate at higher field than almost any other protons and are not likely to obscure part of the spectrum. At the field we are using, tetramethylsilane absorbs at exactly 60 million cycles. Chemical shifts are measured either in cycles per second or parts per million from the position of the standard arbitrarily chosen as 0. If we measure chemical shifts with respect to TMS, the protons of hydrocarbon methyl groups are found at approximately 54 cycles, and protons of methylene groups near 75 cycles. Chemical shifts in cycles per second are proportional to the magnetic field, and it is more convenient to express the shifts in parts per million, or delta, which is independent of the field. To convert chemical shifts to parts per million, the shifts in cycles per second are divided by the radio frequency in megacycles, in this case 60. Thus, the chemical shift of the methyl group is 0.9 parts per million, and the chemical shift of the methylene group is 1.3 parts per million. Another common unit, called tau, is defined as 10 minus delta. On the tau scale, the methyl group has the value 9.1, and the methylene group has the value 8.7. Protons in other groups, for example, methoxyl, olefin, aromatic, and aldehyde protons, also have characteristic chemical shifts, shown here in cycles. Shifts to higher frequency or lower field are shown as shifts to the left in a spectrum. Attaching electronegative atoms to a carbon usually makes the protons on it absorb at lower field, since they are less shielded. For example, although methylene protons in saturated hydrocarbons resonate at 1.3 parts per million, the methylene protons in diethyl ether are shifted to lower field by the electron withdrawing effect of the oxygen atom and resonate at 3.7 parts per million. The methyl group is shifted less and moves from 0.9 to 1.2 parts per million. The area under an absorption peak is proportional to the number of protons which cause the absorption. For example, in diethyl ether, there are 6 methyl protons and 4 methylene protons. The areas under the corresponding absorption peaks are in the ratio of 6 to 4. Therefore, from the spectrum, we can get information not only about the environment of the different protons in a molecule, but also about their relative abundance. We have just seen how the surrounding electrons can change the local magnetic field at a nucleus. Now let's see how the field of one proton can influence a proton on the next carbon atom, a phenomenon called spin-spin coupling or splitting. Proton A requires a field HA to make it resonate. If there is no neighboring proton, A will resonate when the applied field H0 equals HA. The field of a neighboring proton, B, will influence the field felt by A. If the field of B adds to H0, H0 must decrease to keep A in resonance. If the field of B subtracts from H0, H0 must increase to keep A in resonance. In the spectrum, if A has no neighboring proton, the absorption will appear at HA. If the neighbor B adds its field to H0, a smaller H0 is necessary. If B subtracts its field from H0, a larger H0 must be applied. The field of B adds to H0 or subtracts from H0. About half the molecules in the sample have proton B adding its field to H0, and the other half have proton B subtracting its field. The peak for proton A is therefore split into 2 lines of equal intensity, called a doublet. Exactly the same considerations apply to the resonance of the B proton, which also appears as a doublet. Let us review. The spectrum of the A proton is influenced by the alignment of B. One alignment shifts it downfield, the other upfield. The spectrum of the B proton is shifted downfield by one alignment of the A proton and upfield by the other alignment. Thus, the resonance for each proton appears as a doublet. The separation between the lines of both doublets is the same and is called the coupling constant J. Returning to our example of diethyl ether and looking at the spectrum under higher resolution, we see that the methyl protons actually appear as 3 lines, called a triplet, and the methylene protons as 4 lines, called a quartet. The reason is that each group of protons is split by the neighboring protons. Look at the methyl peak. there are three possible alignments for the two neighboring methylene protons. Both may be aligned with the magnetic field, both may be opposed, or one may be aligned with and one against the magnetic field in two different ways. The methyl resonance is thus split into three lines with intensities of 1 to 2 to 1. In the same way, the methylene protons, which have three neighbors in the methyl group, can have them aligned in four different ways. All three may be aligned with the field, all three may be aligned against the field, two may be aligned with and one against the field in three ways, and two may be aligned against and one with the field in three ways. The resulting resonance is a four-line pattern with relative intensities in the ratio 1 to 3 to 3 to 1. Again, the separations between the lines are the same in both patterns. In general, if a given group of protons has n equivalent neighbors, the resonance will split into a symmetrical pattern of n plus 1 lines. These simple patterns occur only if the chemical shift is very much larger than the coupling constant. Otherwise, the patterns are more complex. Spin-spin coupling is transmitted through bonds, not through space, and does not normally reach beyond protons on adjacent carbon atoms, that is, 3 bonds. Coupling through 4 or more bonds is usually very small. Protons which are chemically equivalent do not split each other. For example, the 6 protons in benzene appear as a single sharp line. The same holds true, for example, for the 12 protons in cyclohexane and the 4 protons in methane, and only a single sharp line is observed in each case. In summary, from the NMR spectrum, we get 3 important types of information. First, the chemical shift, which tells us that our diethyl ether example has methylene protons on a carbon attached to an oxygen, and methyl protons. Second, the relative areas, which tell us that the relative abundance of these protons are 4 to 6. And third, the spin-spin splitting pattern, which tells us that each of the methyl protons has 2 equivalent neighbors, and each of the methylene protons has 3 equivalent neighbors. Now that we have explained some of the features of an NMR spectrum, let's look at an instrument and see how the spectrum is actually recorded. The NMR spectrometer consists of 2 parts, the console and the magnet. The console contains the recorder on which the spectrum appears and controls for the instrument. The controls are in 5 main groups. The first group controls the magnetic field homogeneity. The second group controls the intensity of the radio frequency field. The third group controls the receiver and the spectrum amplitude. The fourth group controls an electronic integrator for measuring peak areas. And the fifth group controls the recorder. The sample is placed in a glass tube and inserted in a small air turbine. The assembly is then placed between the poles of the magnet. An air jet is then turned on, which makes the sample spin to average the magnetic field in all parts. Before we take a spectrum, we must adjust the instrument. This is the methyl triplet of diethyl ether. The spectrum appears to be very broad, which means that the magnetic field is not the same in all parts of the sample. To correct this, the magnetic field homogeneity is adjusted. Since all parts of the sample now feel the same magnetic field, the peaks become sharp. Next, the sweep width and offset controls are adjusted. These controls may be set so that the whole spectrum, or any desired part of it, fills the chart. If the spectrum is weak, as with dilute samples, the absorption peaks may be hidden in noise. A great improvement in signal-to-noise ratio may be obtained by increasing the intensity of the radio frequency field and by adding filtering as necessary. Filtering, or damping, simply makes the recorder pen respond more slowly so that it does not follow the high-frequency noise. The time for the scan is then chosen. For weak signals, a slow sweep is desirable. Now we are ready to record the spectrum. Here we see the spectrum of diethyl ether, with its now familiar quartet, caused by the methylene protons split by the 3 neighboring methyl protons, and the methyl protons split into a triplet by the 2 neighboring methylene protons. The areas under the peaks in the spectrum can be measured by electronic integration. The height of each step in the integral curve is proportional to the area of the peak below it and to the number of protons causing the absorption, in this case 4 to 6 or 2 to 3. Now let's use the instrument to solve a typical organic structure problem. Assume that we are given a compound which we know has the formula C2H4Cl2. For this formula, there are only 2 possible structures. 1,2-dichloroethane and 1,1-dichloroethane. Take a moment to picture the NMR spectrum of these 2 compounds. Now let's record the spectrum. We see one peak far downfield with a chemical shift characteristic of a proton on a carbon, which also bears strongly electronegative atoms. This peak is split into a quartet, which means there are 3 protons on the adjacent carbon atom. At high field, there is a larger peak with a chemical shift characteristic of protons in a methyl group. This peak is a doublet, so the methyl protons have only 1 neighbor. Integration of the spectrum shows that the smaller and larger peaks have relative areas of 1 to 3. Thus, there are 3 protons split into a doublet by 1 neighbor, and 1 proton split into a quartet by 3 neighbors. One 1,dichloroethane has a methyl group attached to a carbon with 1 proton and is the unknown compound. The spectrum of its isomer, 1,2-dichloroethane, is quite different. All the protons in this compound are equivalent, so that the spectrum is a single sharp line. Many structural problems involve more complicated molecules. Let us look at the well-known drug cortisone acetate. This compound has a very complex NMR spectrum. Methyl groups are the most prominent features of this spectrum, which has 3 sharp peaks caused by methyl groups A, B, and C. Other protons can be distinguished. For example, the OH proton, the olefinic proton, and the methylene next to the acetate group. Even this partial assignment is of great value in determining the structure. In addition, this spectrum serves as a kind of fingerprint for cortisone acetate. We have mentioned only a few applications of NMR. In addition to structural determinations, NMR is increasingly used in qualitative and quantitative analysis and in the study of kinetic processes. In the short time since it was introduced, NMR has become indispensable to the chemist.